Hi everyone. In the previous lecture, we started off with our discussion on the voltage comparators. We said a comparator at its heart is a very high gain amplifier with a nonlinear saturating characteristics as shown here. And we also said commercially comparators are sold as chips, and one commercial example of a commercial comparator chip is the LM393 chip. And we also discussed in the previous lectures that Opamps are sold as the 741 series of Opamp chips. I mean, there are a wide range of Opamp chips, but 741 is the popularly used Opamp chip. One question that should naturally arise in your mind is that if a comparator is also a very high gain amplifier with a saturating characteristic, why should why should you see a separate chip for these comparators? Okay, 393 series of chips. Why do we need them separately? Why can't I just use the Opamp 741 Opamp itself as a voltage comparator in all my comparator applications? So in this lecture, we'll try to understand the difference between the 741 and the 393 amplifier circuits. I'll also take you through the popular comparator architectures, circuit architectures that were used in the past 15 years or so. So when I was a student, my undergraduate project was to design a comparator. In fact, I worked on two circuits. One was building ring oscillators and the other one was building pipeline ADC. I was part of the project where we built a pipeline ADC, and I had to build a comparator circuit for it. So I'll take you through the comparator circuit that I built, and also the comparator circuits in modern high-speed data conversion circuits. So first, to understand the difference between an Opamp and a comparator, we need to look at the circuit schematics of the Opamps and comparators. Shown here is the schematic of the 741 Opamp. And we will not go in depth, I will not analyze the circuit rigorously, but I'll show that the first stage is a differential to single-ended output. Right? It's kind of an amplifying stage which acts like a differential input to single-ended output stage. The second stage is where you get all the amplification from. The second stage is kind of a common emitter amplifier configuration. Okay, it has some kind of a cascade structure. It'll act like a kind of a common emitter amplifier, which will give you the very high gain needed from Opamps. The third stage, see here, this is the second stage. The input goes to this node, and this here is the output, the pre-final output node. So this goes to your the final output driver stage, which is a common collector configuration. Common collector configurations don't provide you high gain, but they offer you very low output impedances, which is needed for the 741 Opamps. Right? So it's not surprising. You need multiple stages of gains to achieve very high gains. So that's why you see first stage, then a second stage, and finally a third stage for driving the output loads. And also you see a compensating capacitor of 30 picofarads here. Now let's look at the circuit level schematic of a 393 chip. If you look at the circuit level schematic, the inputs are fed here. These are the two inputs, and this is your final output stage. The first inputs are fed to two common collector amplifiers, differential common collector amplifiers. Since common collector gives you a gain of 1, I'll ignore these two. I can ignore these two. We'll talk in a few moments why this is needed. Okay, we'll ignore these two. The input signal, then if you look at it, this is your common emitter differential input pair. It's a PMOS input pair, but PNP input pair, but it's a common emitter differential pair which will give you very high gain. It converts the differential input to a single-ended output, and this single-ended output is fed to a common emitter amplifier again, which is a high gain amplifier. That output is then fed to another common emitter amplifier, which is again a high gain amplifier, which is then fed to another common emitter amplifier, which is again a high gain amplifier. Okay, so here if you see, you have nearly cascade of four common emitter amplifier stages. First stage is a PNP common emitter. The next three stages are NPN common emitter stages. So let's not worry, the output here is floating. It's called as the open collector output. I'll talk about it later. don't worry about the output being floating right now, just treat it like a common emitter stage. And if you observe here, there is no compensating capacitor here. If you see, right, there is no extra capacitor, it's just transistors and cascade of amplifier stages. There is no compensating capacitor. That's the big difference between these two stages. So to understand that, we'll just go back to basics. If you want to achieve high gain, right, see, Opamp is also high gain amplifier, comparator is also high gain amplifier. How do you achieve very high gains? From first principle thinking, you will have to cascade a series of single stage amplifiers. That's how you get high gain, right? You cascade a series of amplifier stages, you get very high gains. Now in case of 741 op-amps, the circuit designer knows that the 741 op-amp will be used in negative feedback. Therefore, when you cascade multiple high gain stages and you know that this amplifier is going to be used in negative feedback, you run the risk of pushing the amplifier towards instability. You know, from basic control theory, for example, let's assume the 4 stages, each stage has 1 pole each. So totally you have 4 poles in the open loop. So if you have 4 poles, all these poles are in the left of plane. So the open loop, the system is stable. But the moment you put it in negative feedback, now we know, I'll just draw the root locus of this. The root locus will look somewhat like this. If your gain is very high, so as you increase your gain, the 2 poles will go into the left of plane, they become complex and go into the left of plane. 2 poles will go into the right of plane, they also become complex. For very high gains, the closed loop poles will be, 2 poles will be in the RHP, the right of plane, and 2 poles will be in the left of plane. So you see here, even though they are stable in the open loop, they become unstable in the closed loop. The poles are now in the right of plane, the system becomes unstable. That is why the 741 op-amps are frequency compensated. You apply frequency compensation because you know that the 741 op-amps will be used in closed loop. So therefore the circuit designers designing them, or the op-amp ICs that are being shipped for commercial applications will be frequency compensated. Okay, and that's why you see that capacitor, the Miller capacitor in the first circuit, and you don't see that in the second circuit. So when you frequency compensate, what happens when you frequency compensate? I'll talk about Miller compensation very briefly here. Okay, again, I'll not go into the details. When I offer a course on op-amp design, I'll go into great detail about Miller compensation. But right now I'll take you through Miller compensation very briefly. What does Miller compensation do? So let's start with an open loop transfer, the open loop frequency response. The open loop has 2 poles here, omega P1, omega P2, which are close by. When you have 2 poles which are close by and the gain is also very high, near the UGB the phase shift will be very close to, the overall if you plot the phase response plot, the phase shift will be close to 180 degrees. And if your phase shift is close to 180 degrees, you are close to becoming unstable. So what do? We employ this frequency compensation technique called the dominant pole compensation. In dominant pole compensation, we make one pole intentionally a very low frequency pole. By doing so, the UGB, the unity gain frequency, will occur even before the second pole. So near the UGB, near the unity gain frequency, this amplifier frequency characteristics, the frequency response will look like a first order system. And first order systems are inherently stable. If you have a single stage amplifier and you put it in feedback, you don't have to worry about stability there. They will always be stable. So we try to emulate a multi-stage amplifier, the behavior of a multi-stage amplifier as a single stage amplifier near the UGB. Then it becomes stable. By doing so, of course I stabilized my amplifier, but I lost out on the bandwidth of the system. The UGB was previously at a higher frequency, now it shifted to a lower frequency. So I traded off speed for stability. So that's the problem with op-amps. If I use an op-amp 741 IC for comparator applications, it will not be able to meet the high frequency, it cannot be used for very high frequency application. See, I want the output of an op-amp, the output of a comparator to suddenly change. I want its output to change suddenly from minus VSAT to plus VSAT. But if I do frequency compensation, I'm trading off the bandwidth. Okay? Therefore, the output will have a certain speed limitation. A comparator always operates in open loop. Right? That's how we began with the definition. By definition, a comparator, even though it's how a comparator structure is, I mean, the transfer characteristics of a comparator is the same, we know for a fact that it is always used in open loop, or it will be used only in positive feedback. Therefore, you don't have to worry about frequency compensation. You just keep cascading as many amplifier stages as you like. Okay? That's what is done here. That's what you see here. You have cascaded 4 stages here. Stage 1 is a common emitter differential to single-ended output. Stage 2 is a common emitter amplifier. Stage 3 is a common emitter. And stage 4 is also a common emitter amplifier. You have 4 common emitter cascades to achieve very high gain. So their goal, the comparator designer's goal, is to give you as high a gain as possible. That's it. They don't have to worry about stabilizing the amplifier at all. Whereas a 741 op-amp, because it's going to be used in negative feedback, you have to stabilize it. And when you stabilize it, its frequency characteristics changes, its bandwidth becomes lower. Okay? So, but you want for your comparator's output to change as fast as possible. So that's the big difference. The difference comes from the fact that one is used in open loop, other is used in closed loop. So again, like I'm talking about a commercial comparator chips, most comparator chips come as dual comparators. So you get 2 comparators in a single chip, and they also come as 8-pin chips in different packages. You can browse through TI's data sheets. There's 393 series, and you will see the different kinds of packaging that they come with. So what should you look for in a comparator? Because you are comparing 2 voltages, you want, for accurate comparison, the offset voltage should be really low. So low offset voltage is one good characteristic of a comparator. Lower power, if there is any DC power that's being dissipated, or even if power is being consumed during the comparison purposes, preferably you want to keep the power as low as possible. Okay? Again, low power is something that's true for any analog or digital circuit. Minimize the power. So this is not a big deal, but lower offset voltage matters to us. Okay? Next, wide supply voltage range, meaning your comparator should be able to, this comparator chip should be able to operate even if I change my supply voltage by a wide range of voltages. Say if I want my comparator to drive a digital circuit, I may want to use the supply voltages of the digital circuit for my comparator as well. Then my comparator should operate properly for this digital supply voltage range. Okay, so that you will see that in the data sheet, what will be the range of supply voltages that you can apply. So this chip, I mean the LM393 chip, happens to be a unipolar IC, which means the output can be between 0 and VDD. So, and you can change your VDD over a wide range of voltage levels. And the circuit should still work and provide you high gain. The third, this is another very important parameter called large IC. The input common mode range for these comparators should be very high. Why is that? Because these comparators can be used by any designer, any circuit designer, system designer in different applications. And they may want to compare your input signal level to some DC level, and this DC level can go from 0 to VDD. Okay, so remember, a comparator becomes active when your input signal approaches the reference. That's when your comparator goes into the high gain region, which means this amplifier should have very high gain for a wide range of common mode voltages. I mean, see, the differential voltage is 0, but the absolute values of Vi and Vref can be anything. Okay, so that's why you want this circuit to provide you high gain when Vi, it needs to amplify when Vi is very close to Vref. So meaning I can apply some common mode at Vi and some incremental signal. I can treat my input signal as some common mode signal Vref plus a delta V being applied to this. Okay, so this comparator should give you very high gain for a wide range of the reference voltage levels. The reference voltage can go from as low to as ground to as high as the supply voltage. So therefore, by design, the circuit designers who design the circuits will keep this in mind, that the comparator should have a wide input common mode range. Then you don't have to worry. You can apply any reference voltage signal that goes from ground to VDD. If I say the inputs ICMR is rail to rail, then you can apply a reference signal anywhere from ground to VDD. Otherwise, if I tell you the reference voltage has to be between minus VDD by 3 to plus 2/3 VDD. If it goes between 2/3 VDD to 1/3 VDD, then naturally that comes as a spec for, as a circuit designer, if you are going to use this comparator whose ICMR is between 1/3 VDD to 2/3 VDD, then the reference voltage that you can use, the reference voltage that you can connect to this comparator should be in this range. You can't use it as a comparator for any voltage range. Okay, so that is something to keep in mind. So a large ICMR is preferred. Ideally, a rail to rail ICMR is preferred. And the output voltage level should be compatible with CMOS and TTL logics. So this is something you will read from a data sheet. See the output voltage levels, minimum and maximum output voltage levels, and that also depends upon the supply voltage. If your comparator can operate on a wide supply voltage range, it can in theory produce a wide output voltage levels as well. Okay, and I think I missed out one thing, which is high speed. Speed is another very important criterion. How fast? If your input signal comes very close to the reference signal, how fast does this comparator transition? Okay, how long does it take to transition from one state to a different state? This speed will matter when you are going to use them in circuits like analog to digital converters, where you will have to perform this comparison operation within half of the cycle, half of a sampling clock cycle. So their speed matters as well. So this is, see, when I'm talking about these limits, these are all for discrete comparator ICs. If you're going to pick a comparator IC from the available commercial products, you have to look for all these numbers. Okay, you have to look for all these specs on the data sheet.